Today we'll just be taking a look at the normal distribution and some of its special properties. So we say a continuous random variable x has a normal distribution with mean mu and variance sigma squared if its PDF is given by, this equation here, where f of x equals 1 over sigma root 2 pi times e to the negative 1/2 with x minus mu over sigma squared, right? Now, first you'll see that we define the distribution with its mean mu and variance sigma squared, right? So it's a bit strange. You should also notice here that we place no restrictions on x, right? So our PDF is valid over all the reals, forever, to infinity and to negative infinity. And also here you should see that we're symmetric around the mean. Our mean mu, right? So we also have this peculiar x-axis here, and that might be hinting, about something in the future here. And finally, I should say that we are really dealing directly with our standard deviation sigma, right? Which determines how fat our PDF is, right? So the larger sigma, the fatter this gets. Now, I get that some of you might be disappointed here to see that there's no closed form for our CDF, right? This is directly from the definition of our PDF and the definition of CDF, right? There's nothing, there's no easy antiderivatives here. But that's really okay, because you'll see later we have a couple of tricks to get around that. But for now, right, we'll just leave it at this, and we're going to move on to the MGF. Take a look at this, but we're going to move on to MGF in a moment. And since we define the distribution with its mean and variance, there's not really any point of deriving them. So pause the video here if you'd like to find the MGF on your own. There is a closed form solution, unlike for the CDF, and it's largely an exercise in algebra. So, yeah. So when x is normally distributed with mean mu and sigma squared as our variance, our MGF is given by this equation here, right? Where we have e to the mu t plus 1/2 sigma squared t squared, right? And this follows directly, from the definition of the MGF that I'm just restating here. And then here I'm just plugging in our PDF. And I get this, right, due to the properties of exponentials because, right, we had an e to the negative 1/2 term, right? So I'm just, this is an easy simplification here. And now, in this step here, we're just completing the square and the exponent. And if you can't see, how we got this, you should verify that yourself. And it's really just algebraic manipulation. But here's the real trick here. So from there, we just plug it back in, right? Because our two exponents are equal. And then I take out the first half of the exponent, this guy. I take him out because it's constant, right? Since we're differentiating with respect to dx, remember. So since there's no x terms here, I can move it forward. And now you'll notice that this guy, right, is just normal with this as our mu, with this ugly guy right here as our mu, and sigma squared as our variance, right, because we have this here. So yeah, by the properties of probability, you know that this guy integrates to 1, so you get our variance, and we're done. So there's two things on this slide, and this is really probably the most important thing to remember about the normal distribution. So first I'm just going to go over, this is the standardization formula right here. And it's just a way to convert any normal distribution to a standard normal distribution. And if you don't know what a standard normal is, right, it's this guy. So it's a normal distribution, centered around 0. So with mu 0, mean 0, expectation 0, and variance 1, right? And since by the properties of the MGF, right, I prove this works for all normals. That's what I do here. And, this is pretty straightforward, but really you should just focus on how much this simplifies computing probabilities of normals, right? So remember, we don't have a closed CDF, and our PDF's kind of weird. So we do need every bit of help we can get here, right? So the second thing on this slide, right, is our 68, 95, 99.7 rule. And this is just a rule of thumb. Remember, I drew your attention to the x-axis in our PDF graph, right? So you should definitely memorize this rule for the exam. And what it does is it lets you estimate the probabilities of normal distribution without a calculator, right? So 68% of the area under the curve is within 1 standard deviation of the mean, right? 95 about is within 2. 99.7 about is within 3, right? So it's really not more complicated than that. And yeah, this is true for all normal distributions because all normals can be standardized. That's a direct result of this guy. But be careful here, right? Because if a problem asks you for the probability of being 1 standard deviation above the mean, right? It's not 68% anymore, or 68.2% or whatever. It's 34.1% because I'm in this guy, right? So they're going to try to trick you with that's how they get you, with the wording there. So in a moment, I'll show you a generic normal distribution type of problem, that you'll definitely be asked. So if we're looking at a normally distributed variable with mean mu and standard deviation sigma, and we want the probability that x is less than or equal to some value a, right? We can just think about a as mu plus delta, and then use our standardization formula to convert it to a standard normal. So if you don't get that right, really our goal at the end of the day is to, if we want to estimate this without a calculator, is just to rephrase this as how far am I from our mean, and then use my 68, 90, 95, 99.7 rule, right? So if you look at this, right, notice that delta is the difference from the mean. So if delta is sigma, right, from this result, we see that we just care about 1 standard deviation above the mean. And then we just use our 68, 95, 99.7 rule. And, we can find any problem here. So if delta is less than 2 sigma, but greater than sigma, right, notice that we're between 1 and 2 standard deviations from the mean. So, you have to adjust your rule for that a bit, and you can eyeball it based on how far it is. But really, spend a minute here, try to understand what's going on. You will be asked this on a test, phrase like this, virtually identical to this. And the key is remembering, okay, this is how I reframe it to be standard normal. So take your time, and I'll see you in a moment. So here, I've just given you guys some practice problems of varying difficulty, and I really do encourage you to give these a shot. But yeah, thanks for listening. Feel free to ask your questions in the comments below, and please do let me know if I made any mistakes at any point in this video, and I'll see you guys next time.